video. If you remember, we had the path foundation uplifted in almost a third of the left part here. You can see the positive values are tension and the negative values are, this is the deformation. The positive values are upward and the negative values are downward. So as you can see, this section is upwarded and it is in tension, and we have some tension forces in springs, underneath the springs. If you go to 3D, you can clearly see that the arrows are different in these two sections. These are in compression, these are in tension. So you can see this part of the foundation is in tension underneath. It is not in agreement with the reality, because in reality, when the foundation uplifts, the underneath is not anything between the foundation and the soil. So it can uplift, but there should not be any force between the surface of foundation and underneath soil. That's the reason we need to somehow simulate this in our model, which obviously it's not working like this. It's intention in this module. Um, the reason is because our system works linear. However, if I just save it and unlock it, and I save as a new module like the same name and nonlinear spring. And I want to tell you what is nonlinear spring. With nonlinear spring, you can simulate this effect that any um, any spring in tension should be eliminated. In this case, as you know, we have two load cases, live, dead, and live. They are fine. We go to load case. Again, we have dead and live. You can create a new case. I just name it nonlinear case, nonlinear spring case. And here I go with nonlinear static. Here I add dead load with a factor of 1.35 and live load with a factor of 1.5. And press OK and press OK. In these cases, when I use nonlinear cases, the load combinations are not useful. So in other words, the load combinations are not valid. We cannot linearly add two load combinations in the case of nonlinear analysis. That's why I just delete them. And I go to the spring properties, area springs. You know this, AS is spring 1. And you can see here, these four options work only in the nonlinear case. All of the previous cases were linear analysis, which obviously, that's why the springs work in both compression and tension. But if you want your springs to work in compression only, you need to do nonlinear case. That's why when I'm doing nonlinear case, this part will go through and the springs will work compression only. So if I analyze the structure to see if my intention is correct, and we will have all the springs in compression, nothing in tension. So let's see what happens in the analysis. Okay, here we are. So the display menu, show the form shape. I want to see nonlinear spring case. I don't do anything with the combos here. So this is the nonlinear case, and you can see from green stuff and blue stuff, they are in tension. I mean, they are uplifts. So you can see from here, it's uplift, almost half, a bit less than half. So if it goes beyond half, literally the structure will be unstable. So the area of uplift is more. And this is obvious because when we don't have those tension springs are still acting like a glue between the foundation and soil. And that's why in the previous case, you had a third of left, I mean, a third of the whole foundation uplifted. But here you have almost a little bit less than uh, half of the foundation. And if you take a look at the spring forces, in the case of not combo, in the case of nonlinear spring case, you can see that you don't have any spring here because they were in tension and they were eliminated. So you have only springs in compression, which are these. So this is more a sort of more realistic uh, simulation of the foundation. So in reality, what happens is like this, and just a quick design approach reveals some interesting results as well. For example, for the design, first go to the design combinations, and these are the load combination, the conventional load combination. I don't need them. I don't want them. That's why I go to the load combination and add one combo one, and I say the nonlinear case with a scale factor of one. Okay, this is my own load combination, but these two, if I delete them, they will be there again because they are added automatically based on the default load combinations. So if I go to the design combinations, I can put them out of the basket and I can put combo one into the basket. This is my own load combination, so I want the design to be based on my own combo one, which is the nonlinear case. So if I go and start the design is only based on one load combination, which is the nonlinear case. So if you go to the detailing, you can see that. Okay, you can see that the reinforcements increased in comparison with the previous case. And you can see it's H20 at 90 millimeter and H20 at 220 millimeter in addition to the top reinforcement. So you need top reinforcement here as well. And if you go to the 3D, you can see this is the arrangement of the reinforcement for this pad foundation based on a linear case. And you can see a concentration of reinforcement here because it's in compression, and you have top reinforcement and lack of reinforcements here because it's just uplifted. However, in reality, in this example, the my, the moment, are associated to the dead and live load. But in reality, if you have some my or mx from wind load, which is lateral load, they should be in a positive and negative sign. So we have positive wind x, negative wind x, positive wind y, negative wind y. So if you include all of those cases into the analysis, then you will have this concentration of reinforcement everywhere, not only here. So this is a result of having only one load case, which is nonlinear case, and all of the MYs are in positive direction. That's why the result is like this. Otherwise, in your coursework, when you have wind X and wind Y, and you can have both of them into the calculation, the distribution of reinforcement will be more rational. So we will touch to this sort of analysis in your coursework as well later on. Thank you for watching.